Swayam Prabha. Digital India. Educated India.
So, in this lecture, I will start the next topic, that is the settlement of the foundation, because I have discussed about the soil exploration, then the bearing capacity of the foundation, then we will go for the settlement of the foundation, because as you know that the two design criteria for the foundation design is the bearing capacity and the settlement. So, I have discussed the different bearing capacity theories and the different cases like incline load, eccentric loading case, then the layered soil case, the effect of soil compressibility, then the tilting base case, then the sloping ground case. So, all the cases are discussed in the bearing capacity part, and I have also discussed that which theory you should use for what condition, okay, because and then I solve the number of example problems to show you how you can incorporate those theory and how you can use those theories to calculate the bearing capacity under different loading condition, different soil condition, different foundation conditions. Okay. So, now today I will start the second part, that is the settlement of the foundation, how you can calculate the settlement of a foundation. But before I start that part, so I will just discuss one small part that is remaining, that is the fourth case for the layered soil bearing capacity. So, first I will discuss that fourth case and then I will go for the settlement part. So, now if I go for the case 4, so in the case 4 of that layered soil, where the loose sand on stiff clay, okay. So, loose sand on the stiff clay, that means here your top layer is the weaker layer and the bottom layer is the stronger layer, because previous three cases always the bottom layer is the weaker layer and the top layer is the stronger layer, but it is the opposite case. So, in such case I will give the expression for three different footing condition, that means the strip footing, your rectangular footing and then the circular footing, and if you have the equation for the rectangular footing, you can get the equation for the square footing also. Okay, so, now the first one is the strip footing. So, in this case QU is given as half gamma 1 B in gamma dash. Now, what is this case particular? This is the foundation, okay. This is the ground surface and this is my stiff clay and this is loose sand. So, this is here C equal to 0, here phi equal to 0. So, now in previous case where this was simply the opposite, that means the stronger layer is on the top and the weaker layer is the bottom. So, there is a punching type of failure was considered, but here the stiff layer is the bottom. So, this stiff layer is considered as a rigid layer, okay. And then in this case the failure will be most of the cases on the top layer, okay. So, that is why it is calculated that this is the bearing capacity of the top layer, half gamma 1 B gamma n gamma dash plus, because this is the third term basically. So, I should write the second term first, then the third term. So, the second term, this is gamma 1 df into n q dash. So, this is df, okay, this is the first layer, then plus the second third term gamma 1 b in gamma dash. Okay, so, this is the first term is 0 because c is equal to 0, then second term and the third term are given. Okay, so, this is the q u and that should be less than equal to q b, because definitely that cannot be more than the bearing capacity of the bottom layer, because in previous three cases this should not be greater than q t, because in that case the stronger layer was the top layer. So, it should not be greater than q t, but now this case the stronger layer is the bottom layer. So, it should not be greater than q b. Okay. So, now what is q b? Now, q b will be equal to, now if this is the case, then this is C n C 2 C 2 n C 2 plus gamma 1 df. So, q b is considered as gamma 1 df, because as I mentioned here, where the h part is not considered. Okay. So, now if you consider the gamma 1 df plus h, then you have to subtract that h in from the main equation. So, that is not given. So, that is given in q b term. So, h term is not considered. So, that is why it is gamma 1 df into C 2. So, because that h term is already within that bearing capacity equation, it is incorporated. So, this is the equation for the strip footing. Now, for the circular footing, the equation will be q u is equal to gamma 1 df n q dash, then this shape factor is introduced, s q dash, then it is same half gamma 1 b n gamma dash, then s gamma dash, b or d, then s gamma dash. So, this n gamma dash, s q dash and s gamma dash, these are the shape factor, and that should be less than q b, and then the q b should be equal to that 1.2 C 2 N C plus gamma 1 df. Okay, same as the strip footing, only the for the square footing 1.2 term is introduced. This is N C 2. Now, I can write the equation for rectangular footing. Okay, so, this is q u, this is half. Let me explain the write the second part first, then I will write the first part. The same as gamma 1 into df, then n q dash. Now, the shape factor again we have to apply, and that is 1 minus s q dash into b divided by L. Then the third term, that is half gamma 1 b n gamma dash, then 1 minus s gamma dash into b by L. That should be less than q b, and the q b is equal to 1 plus 0.2 b by L, then C 2 N C 2 plus gamma 1 df. So, this way I can calculate the bearing capacity for the fourth case, okay, where the steep footing, circular footing and rectangular footing. Now, how I can calculate the n q dash, n gamma dash and s q dash, s gamma dash. So, from this chart. So, these two chart will give you the bearing capacity factor as well as the shape factor. For example, see this dotted line is given n q dash and the farm line is given n gamma dash. Okay. So, these are the value h by b, that means the thickness of the footing. So, this h by b, so this is h, this is the b, width of the foundations. Okay. So, this is width of the foundation, this is the h. So, this h by b, if I know the h by b, then this is the internal friction angle of the obviously of the top layer, then this value h by b is 0.2, this farm line is given for n gamma dash and this dotted line is given for n q dash, these are the value. So, this is for different friction angle, this is these two for 0.42, this is 0.4, then 0.6, then this line is 1 and this dotted line is also for 1, then this farm line is up to 1.5 and dotted line is 3. So, that means h by b for farm line is up to 1 point, farm line is given 1.5 and dotted line is given up to 3. So, these are the values. So, from here you will get the modified bearing capacity factor. So, these are called modified bearing capacity factor. So, from this chart you will get the n gamma dash and n q dash, and similarly you will get the s q dash and s gamma dash by using this chart. Again this is h by b and the farm line is given for s gamma dash and the dotted line is given s q dash. This is for 0.21, 0.2, 0.4, 0.6, 1 and 2. So, this way and for different friction angle value. So, this way you will get the modified bearing capacity factor and modified shape factor to incorporate the fourth case, that is if the top layer is loose sand and the bottom layer is stiff clay, then how you can calculate the bearing capacity. So, this chart you can use and you will put this chart in the equation which is given, and then you will get the maximum bearing capacity or the bearing capacity of the two layer case, and you see that these are the equations. Okay. So, now one thing before I finish this part, one thing I want to mention, that in my previous class also when I solve the bearing capacity this two layer case equation. Okay, for here I am taking some loose sand and the soft clay. So, all these terms. So, basically if the soil is loose or medium loose, if it is the soft or medium consistency clay, then always this shear failure will not, general shear failure will not occur. So, there is a possibility that there may be a local shear failures, but the equation that I use during the bearing capacity calculation, I use all the cases, even if when I put the foundation directly on the loose sand or the weaker soil, I consider the all the terms or the bearing capacity factor, those are proposed for general shear failure. Yeah. So, that means I have used all the bearing capacity factor proposed for the general shear failure, even though the soil is weak soil, and I put the foundation directly over there. But actually when this theory was developed, there is no such recommendation is given that it is taken that what to do if the soil there is a local shear failure. Now, one thing I have mentioned, that I have given the compressibility effect part. Now, if those data are available, then you can check whether you need any compressibility corrections or not for your case, your soil case. Now, if you need that, then you put those corrections here. If you have those data, you put those corrections here and then you incorporate the soil compressibility effect also, because that is important, because here we are taking, not all the soils are not the stronger soil, some weaker soil also. That means when, but these recommendations are not given here in original theory. So that means you have to collect those data and you have to check whether some compressibility soil compressibility effect is there, or you have to put those corrections. That is one way. Another way, some researchers, they have suggested that when the soil is weak soil, so instead of taking full C, you take 2/3 of C value, which is recommended by the Tazaki for the local shear failure, the 2/3 of C and tan inverse 2/3 of tan phi. Okay, so you do that part also, because if you are sure that this soil is very poor soil, weaker soil, that means there will be a local shear failure possibility, or this is basically just to reduce the bearing capacity. If I take full C, then I will get a higher bearing capacity obviously, but the soil is weaker soil, and the bearing capacity equation or the factors that I am using, it is valid for the stronger soil or the general shear failure. So to be on the safe side, just to it is reduce the shear strength parameter, that means by the recommendation given by the Tazaki. But actual original theory, as this type of recommendation is not given, so I have taken full C value, full strength parameters I have given. Even in the assignment problems also I will mention that you take full strength parameter value. In the exam also you will take full strength parameter value, but you should know that to be on the safe side, it is better during your design that you reduce this strength parameter value by, as per the either given by the Tazaki's recommendation, when 2/3 of C, or the phi value also you reduce according to that, because when you are putting foundation on the weaker soil directly, specifically because we have to calculate QT, basically we have to calculate QB, and QB soil is weaker soil. So during basically QB calculation, you reduce your, because QT calculation reduction is not required, because QT is your stronger soil. So general shear failure will occur when I am talking about, this is not the layer case, I am talking about when you are calculating the bearing capacity individually for top layer and the bottom layer. So for the top layer it is okay, but the bottom layer bearing capacity calculation, you reduce the shear strength parameters. Okay. Or if you have the compressibility, soil compressibility factors available, or those data are available, you can apply those factors also, depending upon what parameters are available. But for your these examples also, I am taken full strength parameter. In the exam and the assignments also you will take the full strength parameter, but when you apply them in the real design, I would suggest that you can reduce it. But again, it is engineer's choice, engineer's judgment, whether he or she will take the full parameter, strength parameter, or reduced strength parameter. But these are the facts that I have discussed. Okay, so now I will go to the next part, that is the next topic, the settlement of foundation. Okay. So now as you know, there are two design criteria. One is the bearing capacity, another is the settlement of the foundation. So when we are talking about settlement of the foundation, so the initial part, definitely all these parts are covered in the foundation engineering course. So that's why I will not go in detail in this part. Those are already been covered in the foundation engineering course, but for the continuation purpose I will explain them so that there should be a continuation. I did it for the shallow foundation bearing capacity also. I explained initially few things. Those are very common for foundation engineering course. So now those things are similar type of things I will explain in settlement part also. Okay. So that means we have the three major type of settlements that we have to check, that the uniform settlement, differential settlement, and tilt. What is the difference? In uniform settlement, your whole building will settle uniformly, and in differential settlement, suppose some column will deform more compared to the other columns, okay, or few columns will deform more compared to the other columns. So, that is called the differential settlement. And in the tilt, suppose one side of your building will tilt or will deform more compared to the other side of the building. So, that total building will tilt in towards a particular site where the deformation is more. So, that is called tilting, differential settlement and the uniform settlement. So, most of the design if suppose your soil parameters are not significantly varying in your site, or your design or the load of the foundation or design or the load coming on each foundation are not significantly different, or then there is a huge variation in the load coming on the foundation, then also you have to go for the differential settlement check and tilting check also. Okay. Otherwise, if the loading are more or less same coming on the all the foundation, soil properties are more or less same, then generally you only go for the uniform settlement. But if the design load is different or in different column and that difference is significantly very high, then you have to go for other two checks also. And the soil parameter variation is also significant. So, in the settlement basically three types. One is the immediate settlement, consolidation settlement and the secondary settlement. Okay, secondary basically this is primary consolidation settlement and the secondary compression settlement. So, the immediate settlement basically it is elastic settlement, it takes place during the application of loading. So, and this immediate settlement is very in the significant in case of clay sandy soil. In sandy soil most of the settlements are immediate settlements. So, that means you will get the settlement within a 7 days even less than that, because in consolidation settlement, which is a primary settlement for major settlement for the clay soil, because in case of clay soil your permeability is less. So, when you apply the load, soil dissipation takes more time. So, that is why the consolidation is a very major settlement for the clay soil. And secondary settlement is occurs due to volume change or due to the rearrangement of the particles. So, that is secondary compression settlement. So, this is the different cases where I will get the immediate settlement or primary consolidation settlement or secondary compression settlement. For example, the sand, as I mentioned, granular type of soil, immediate settlement is the majority of the settlement. For inorganic clay, primary consolidation is the major part of the settlement, and organic clay, secondary compression is the major part of the settlement. So, in this case, in this course basically we will concentrate or I will concentrate on the immediate settlement and the primary consolidation settlement. So, we assume that our soil is not where the secondary compression settlement will not be a major part, or so that is why we will consider only the immediate settlement and the primary settlement, the primary consolidation settlement. So, now this is the typical chart or the slide where I have given all the methods, almost all the important methods, those are used to determine the settlement of clay soil as well as the granular soil, and I will discuss all these methods. Okay. So, that means the first, the immediate settlement for clay, that I can calculate by using this equation. So, I will discuss what is the different terms of this equation, and then I can calculate the consolidation settlement. So, this is the first term will give you the immediate settlement, then the consolidation settlement, and either I can use this top equation or I can use the bottom equation for the consolidation settlement. So, this is the primary consolidation settlement. So, if I add this immediate settlement and the consolidation settlement, then I will get the total settlement of a foundation resting on a clay. And for the granular soil, as I mentioned, the immediate settlement is the major part of the settlement. So, most of the settlement will take place immediately. So, these methods, these settlements can be mostly calculated by field test data. So, I can get these settlement from directly from the plate load test, method, I can get it from the SPT base method, then I can get it by the SCPT base method, that means the static cone penetration base method. So, if I have the data of plate load test, I can calculate the settlement of a foundation. If I have the data of the SPT value or SPTN, then I will also get the settlement of the foundation. If I have data for the static cone penetration, basically the cone resistance, that's QC, then also I will get the settlement of the granular soil. We can apply the semi-empirical methods also, that is the fourth one, and then we can use the strain influence factor methods, that also will be discussed. So, these are the basically 5 methods. The lower 5 methods can be applicable to determine the settlement of granular soil, but for the immediate settlement for clay we can use the first equation, and the consolidation settlement we can use the second equation. And you can see the consolidation settlement and the method based on SCPT and the semi empirical methods. So, these 3 are more or less same. Okay. So, that is why I will give a example problem to calculate the consolidation settlement only. So, the similar way you can calculate the, if you have the CPT data, SCPT data, then you can calculate the settlement of the granular soil, or you can use the empirical equation also by using these methods to calculate the settlement of a sand. So, now one by one I will discuss this total 7 methods I have mentioned here. 2 are for clay soil and 5 are for sandy soil. So, now these 7 methods I will discuss now. So, for the immediate or the elastic settlement. So, this immediate settlement, this equation is based on the elastic theory, and this is the elastic settlement. So, where SI is the immediate settlement and Q is the net foundation pressure acting on the foundation base. B is the width of the foundation, E is the elastic modulus of the soil, mu is the Poisson ratio of the soil, and IF is the influence factor. And once I will get these things, then because this theory is valid for the surface footing, but if your foundation is placed at a depth, then you have to apply the depth correction. Okay, so that means what are the types of corrections are required? 2 types of correction required. Then the depth correction or the rigidity correction. Now, rigidity corrections, why it is required? That means if you have the influence factor table, you can see this influence factor table, this IF value I can get from this table, where it is given for flexible foundation and rigid foundation. Now, if and in flexible foundation, different types of foundation like circular, square, rectangular, which different LYB value 1.5, 2, 5, 10 and 100, then it is for center, corner, and this is average. Okay. So, that means and obviously, the center one here has the more influence factor. So, center one will always we will calculate the settlement at the center. So, center one is giving more value. So, center, then the corner and the average. So, now if you take the flexible foundation IF value to calculate the immediate settlement for rigid foundation, then you have to apply the rigidity correction. And if you take the rigid foundation IF value to calculate the settlement for immediate settlement for the clay, then this rigidity corrections is not required, because we have taken the IF for rigid foundation itself. But in our most of our design, or basically I prefer to take the flexible foundation center IF value, then you apply a rigidity correction. Okay. Now, what is that rigidity correction value? Now, if you look at these values, that means for rigid footing and the center. So, this is center, it is IF value is 1, and the rigid at the rigid foundation it is 0.86. Because why rigid foundation it is not center, average, corner? Because if it is a rigid foundation, it is expected that the foundation will settle uniformly. That is why only one factor is given. But in flexible foundation it is not like that, because in the center and the edge there will be a different settlement. Okay. So, that is why different values are given. So, now for the square footing it is 1.12 and it is 0.82, 1.1, 1.36, 1.06, 1.52, 1.2. So, if you see that the rigid footing influence factor is almost 80% of the influence factor of the flexible footing at center. You can see roughly 80%. So, that is why, as I mentioned, that what I do, that I take always in the calculation whether the foundation is the flexible foundation or this is a rigid foundation. Generally, the wrap foundation you consider as a rigid foundation or isolated footing, that means the one foundation for one column is considered as a flexible foundation. So, if now I generally prefer to take the IF value of flexible foundation, IF value at center for flexible foundation for all the cases. Now, if it is a rigid footing, then I apply a rigidity correction which is 0.8. So, the rigidity correction factor is how much? The rigidity correction factor is, this correction factor is 0.8. Okay, so, the rigidity correction factor is 0.8 is applied. Once you calculate these SI by using the given value, by taking the influence factor at the center for flexible footing. Now, if it is flexible footing, then the rigidity correction is not required. Now, if it is a rigid foundation, then you apply 0.8 with this calculated immediate settlement. Okay. So, now these are the table by which you can, because you know we should know the N and mu value for the soil. So, these are the tables are given for different soil. So, from this table or you have the E and mu value directly, you can use them, but if you do not have those values, so this table will help you to take the appropriate E and mu value. So, for this table is for the mu value and this table is for the E value or Young's modulus. This is the E value table. So, this if you have the N value SPT, then also you can calculate the E by using these correlations. If you have the QC value in cone resistance, then also you can use this correlation to determine the E value, and you can correlate with E with the shear strength, unrest shear strength, or this is CU or SU or CU, unrest cohesion also. If you know the undrained cohesion of the soil, then by using these correlations also you will get the E value. So, but these are the correlations and you can see these some ranges are given. So, it is always better to have your have the particular E and mu value for that soil for which you are designing the foundation. So, that means you should have the E value and mu value for that particular soil for which you are designing the foundation. So, that is these tables will give you guidelines, but it is better always have the actual E and mu value. Okay. So, now these are the some this is another table by which also you can get the elastic modulus for different types of soil. And then as I mentioned that there is a depth correction factor. Okay. So, this is the rigidity correction factor I have discussed. Now, there is a depth correction factor. So, depth correction factor I can get from this depth correction factor Fox depth correction factor chart. So, this x axis is depth correction factor, y axis this d by root over L by B, and this is root over L by B divided by d. D is the depth of foundation. So, generally the upper part of this chart is used for the shallow foundation design and the lower part of this chart is used for the deep foundation here. So, now for the shallow foundation design most of the problems we will use the upper part, but when you calculate the settlement for the pile foundation, then we will use the lower part. And this is L by B is the L is the length of the foundation, B is the width of the foundation. So, these are the chart from which I will get the bearing capacity or the depth correction factor for this immediate settlement. Okay. So, that means I have discussed the depth correction factor, I have discussed how you can get a value of E and the mu. So, again I am mentioning that if you have the actual E and mu value, that is always preferable, but if you do not have, so these tables will guide you to select the appropriate E and mu value. Okay, so this way I can calculate the immediate settlement. So this settlement will give you the immediate settlement for the clayey soil. So next class I will discuss the consolidation settlement of the clayey soil, and then the other settlements, that settlement procedure to determine the settlement of the granular soil or the sandy soil. Thank you.